So right now you're probably wondering, why is the potential energy negative? Why isn't the potential energy between these two charges positive? Not only is it negative, it's minus 1 billion joules of potential energy. Well, to look at that, let's revisit how we defined potential energy. We define the change of potential energy as being equal to minus the work done in moving an object between 2 points A and B. Let's look at our two charges. We have a positive charge, and let's say we have the negative charge, and they experience an attractive force being opposite charges. Let's focus on just the negative charge right now. So this is the Coulomb force on the negative charge from the positive charge. I'll label the negative charge Q1, or rather I'll label the positive charge Q1 and the negative charge Q2. Let's do a coordinate system where the positive charge is at the center of our coordinate system, the origin. So in other words, our coordinate system is from the frame of reference of the positive charge. If we move the negative charge to a point farther away, the attractive force indeed gets smaller, but notice the displacement is opposite the direction of the Coulomb force as we move the negative charge farther and farther away. If you recall that the work done by a force in displacing an object between 2 points is equal to the line integral of that force, and if we look at this alternative version of the dot product, that is the magnitude of the force, the magnitude of the displacement, times the cosine of the angle between them. Since the displacement vector and the force vector are in opposite directions, the angle between them is 180 degrees. The cosine of 180 degrees is -1. Because the force is a magnitude and the displacement is going to be positive, that -1 means that the work done in separating these two charges is negative. Let's go ahead and indicate that work done like this. We will just say it is equal to a minus the magnitude of the work done in moving those two charges apart. You'll see why I'm putting those absolute values there shortly. Okay, so we've established that the work done in separating the charges is negative because it did involve some charge separation in the thundercloud. Well, if we return to our definition of potential energy, this is equal to minus the work done. And that's not the potential energy at a point. That's the change of potential energy between 2 points. So the change of potential energy as we separate these charges is equal to minus the minus of the absolute value of the work done in separating those two charges. Notice a minus times a minus is a positive. This means that the change of potential energy is equal to the absolute value of the work done, which is a positive value. So what that means here is, even though we have a negative value for the potential energy at the current charge separation, the change of potential energy in separating those charges, assuming they were closer together, is positive. Oh, well, so you might be wondering, well, Mel, the change of potential energy is positive, but you wrote down that the potential energy for this charge configuration for the 8-kilometer separation distance was negative at minus 1 billion volts. How do you explain that, Mel? Well, let's look at a graph of potential energy as a function of separation distance. The vertical axis will correspond to potential energy. The horizontal axis will correspond to separation distance. I'll place right at the origin here, just for qualitative reasons, I'll place our charge Q1 there, and I'll place our negative charge out here somewhere. And this is just for qualitative reasons, so we could kind of imagine how charge Q2 is separated from Q1. So again, we had the potential energy at 8 kilometers was negative 1 billion joules, but we've just established that the work done, but we've just established that the change of potential energy must be positive. And we know we used the function of the potential energy at a certain distance is equal to K Q1 Q2 over R. So what do you think this graph of potential energy versus separation distance must look like? Well, if you said it must look like this, you'd be absolutely right. This is illustrating the potential energy between this pair of charges. Now notice, remember, charge 1 is a positive charge, charge 2 is a negative charge. Charge 2 is a negative charge. The Coulomb force between them is attractive. So if we look at the sketch, this is indicating that attractive forces have negative values of potential energy. Now, again, the change of potential energy is positive. So what does that look like in this sketch? Well, what that looks like is we are getting more and more positive as we get farther and farther away. And that makes sense because the larger the magnitude of a negative number, the smaller that number is. For example, minus 100 joules is smaller than minus 90 joules. Minus 1 joule is smaller than 0 joules. And we defined a point very far away, infinitely far away, as having 0 joules of potential energy. So even though we are at minus 1 billion joules of potential energy, if we continue to separate those charges, the change of potential energy would increase. And that makes sense because you have to add energy to the system in order to separate them. What about if we had like charges? If we had two like charges, well, those two like charges would still follow this relationship, the relationship being the Coulomb constant times the product of the charges divided by the separation distance. So since we are saying, what if we had two like charges, and let's just say that they're both positive charges, and actually for your notes, I'll also say if they are both negative charges. Notice in each of these scenarios, this would correspond to repulsive forces. And those repulsive forces have a potential energy that is inversely proportional to the separation distance. So what that would look like is a curve that approaches zero asymptotically. With that said, we can say then that for attractive conservative forces, they will have a potential energy that looks like this. And for repulsive conservative forces, the potential energy will approach zero asymptotically from the positive direction. So this is for repulsive conservative forces. So it makes sense that the potential energy for this problem, when those charges have been separated to 8 kilometers, it makes sense that this would be a minus sign, that we would have minus 1 billion joules of potential energy, because attractive conservative forces, the potential energy shared by those two objects will be negative.